Hi, this is the continuation of the part 4 of the Zener diode calculations. So, as I have been mentioning in the previous video, the impedance of a circuit is measured in ohms and is represented by the letter Z. And when we say impedance, it means that we have to include both the inductive and capacitive reactance and the resistance because all three are forms of opposition to the flow of current. But of course, we will be focusing ourselves on the Zener diode. So in general, the formula for the calculation of voltage is equal to the product of the current and the impedance. In this case, V is equal to IZ. And in Zener diodes, the VZ is equal to IZ multiplied by the impedance ZZ. So Zener voltage is the product of Zener current and Zener impedance. Again, the Zener impedance ZZ is the equivalent series resistance of a Zener diode when it is conducting current. And it is calculated or computed as a change of Zener voltage represented by delta or triangle VZ that occurs as a result of a tiny change in Zener current, delta IZ. The Zener impedance ZZ should ideally be zero, but in reality, a Zener diode has some impedance. Now, in this figure, you will notice that the VZ is on the left side, close to the VR or the reverse voltage, and this VZ occurs, for example, here from 19 milliamperes up to 21 milliamperes. So if you take the difference between 21 and 19 by subtracting 21 minus 19, that will represent our change in IZ or delta IZ. And if you also consider the change in the VZ, this is represented here. From this point, we may have a small value of VZ and a little higher value of VZ here. And when you subtract that VZ, which is referring to the occurrence of 19 milliampere here, so there will be a particular VZ here, and that VZ for sure is smaller or a little smaller than the point where the 21 milliampere here occurs. So the other point here minus the other point here of the VZ will give us the delta VZ or the change that occurs in the VZ. Now, if you divide the two, VZ divided by IZ or delta VZ divided by delta IZ, we will get the answer for the Zener impedance ZZ. So again, the Zener impedance is inside our Zener diode, and it has its internal impedance and internal VZ. So ideal diodes or ideal Zener diode has a ZZ impedance of 0, while a practical Zener diode has a ZZ or impedance of the Zener greater than 0 or positive number here. So the IR here is the reverse current. Let's see the other formula here, which refers to the calculation of the uh, VR here. In our example, we have the ZZ parallel to RL. So that will be multiplying Z and R divided by Z plus R. So we did not show it here, but when you say ZZ parallel to RL, it means that you have to multiply the ZZ and the RL and then divide the answer by the sum of ZZ and RL. In other words, it will be ZZ multiplied by RL divided by ZZ plus RL. But we will simply write it here as ZZ parallel to RL. And we have another one here, ZZ parallel to RL plus RS. Now, considering this in a shorter form, so approximately this is also the same as ZZ divided by ZZ plus RS multiply by VR, assuming that the ZZ is extremely smaller than the RL. The VR out is called as the ripple present at the regulator output. Again, VR here, small letter R, represents the ripple present at the regulator output. And the ZZ parallel lines here, RL, means that the parallel combination of ZZ and the load resistance. And the RS is the regulator series resistance, of course. And the VR is the peak to peak ripple voltage present at the regulator input. So this one, VR here, is the peak to peak ripple voltage present at the regulator input. So this is about the Zener reduction of ripple voltage. Now, let's say that 1N or IN4736 Zener diode has a ZZT of 3.5 ohms. So it means that the impedance of the Zener diode is 3.5 ohms. Now looking at the datasheet, it gives us the VZT as 6.8 volts and the IZT equal to 37 milliampere, while the IZK is equal to 1 milliamperes or 1 milliampere. What is the voltage across the Zener terminals when the current is 50 milliamperes? So we are we will be trying to calculate the voltage VZ when the current is 50 milliampere. How about 25 milliamperes? So we will be doing two calculations. Now in this first calculations, you will see that the change in IZ is taken by subtracting IZT from IZ, and this will give us a positive value of 13 milliamperes. And when you multiply the I and the Z, then that's to calculate the V. So that's Ohm's law. VZ is equal to the change in IZ multiplied by the impedance ZZT. So we will get a value of 45.5 millivolts. That is because the current is milliamperes multiplied by or multiplied to ohms. Then we have the delta IZ, which will be equal to negative 12 milliampere. That is by doing some other calculations here. Let's suppose that the VZ is calculated first. So we have to get 6.8 volts minus the delta VZ. And the delta VZ is equal to 42 millivolts here, because this one is for the current of 25 milliamperes, because there's two calculations here, one for 50 milliamperes and one for 25 milliamperes. So in the other VZ, we have 6.8 volts plus delta VZ. So we get 6.8 volts plus 45.5 millivolts. That's equal to 6.85 volts. That's the VZ. And this two is when the current is 50 milliampere. On the other hand, the delta IZ equal to minus 12 milliampere, and the delta VZ equals to negative 42 millivolt. This case is for the current of 25 milliampere. So it will be better if we do it again, and this time I'll be writing my solution or in our handwritten form. Let's see. I'll just move this one on the right side first. All right. So again, this is the same given problem, and we will find the VZ here when IZ is equal to 50 milliampere. So to do that, we have to uh, take note the IZ is 50. So IZ minus IZT. So 50 milliamperes minus 37 milliamperes will be positive 13 milliamperes. Now, this is more clear or clearer because I wrote down the substituted values for IZ and ICT. So it's 50 milliamperes minus 37 milliamperes. We got 13 milliamperes. I hope that's clear. So again, the IZ here was taken from here, 50 milliamperes, and the IZT was taken from the given IZT 37 milliamperes in the question. Now, in the case of the delta VZ, or the change in the VZ, we will have to use Ohm's law. So the delta VZ, that the delta IC, I mean, that we calculated here, 13 milliamperes, will be multiplied to ZZT. So that will be 13 milliamperes multiplied by the ZZT, which is 3.5 ohms as given in the question here. 3.5 ohms, then we will be getting 45.5 millivolts. Now, if we go back to the previous slide, that's it. We have here 13 milliamperes and 45.5 millivolts. So whichever is better for you to understand, then you may refer to the slides that you understand more. So if you understand this more, then you can consider this. So this is the calculation for delta IZ, or the change in the IZ or IZ, and this is the delta VZ, which is the changes or the change in the VZ. That is if the IZ is 50 milliamperes. But there are two questions here. So we have to consider VZ when the IZ is equal to 25 milliamperes. So doing the same thing we have here. By the way, I forgot to calculate the VZ. So in other words, the VZ is equal to VZT plus the change in VZ. So the VZT is equal to 6.8 volts. You add the 45.5 millivolts, and we will get 6.8455 volts. That's the answer to this question. Now, you may wonder where I got the VZT. It's given in the question here that the datasheet gives VCT equal to 6.8 volts. Now, in the case of the 25 milliampere value, amperes value of IZ, delta IZ, same formula, IZ minus IZT, but this time the IZ is 25 instead of 50 before. So the answer will be a negative value because the 25 milliampere is smaller than the 37 milliampere amperes IZT. So the delta IZ will now be minus 12 milliamperes. In the case of VZ or the VZ, delta VZ, delta IZ multiplied by ZZT, we will get negative 12 milliamperes multiplied by 3.5 ohm. Again, the minus 12 was taken from the changes in IZ, and the ZZT were taken from the given value in the problem. So we will get a negative 42 millivolts VZ, or if you want to convert it to volt, that's equal to negative 0.042 volts. In the calculation of VZ, we use the same formula, VZT plus delta VZ. We have 6.8 volts as given in the question, 6.8 volts plus the negative 0.042 volts here. Some people have some mistakes in the calculations because of the unit. Sometimes they forgot to put uh, the unit to be volts. So some people might subtract 68, 6.8 volts, 6.8 minus 42, or minus negative 42. Thereby, you will be getting the wrong answer. So take note that negative 42 here is not uh, taken as volt. It is written here as millivolt. Therefore, you cannot subtract directly millivolt from 6.8 volts. That's why there's a need to change our answer from minus 42 millivolts to negative 0.042 volt, which is very small. Therefore, when you subtract that to 6.8, it's negligible, or it's almost like we did not really subtract. But this is the VZ equal to 6.758. So as you can see here, the value of the VZ, whether the IZ is 50 milliampere or amperes or 25 milliamperes, is still approximately the same. So 6.8 rounded, and this is also 6.8 when rounded. Therefore, we can say that the effect of the internal resistance or impedance of the Zener diode is not necessarily be big. So it's negligible, or we can forget about it because it's very small, and it will not defeat the purpose or function of the Zener diode, which is to provide a uh, constant or stable voltage of around 6.8 volts. So that's it for our ERC Tipsnology tutorial or discussion about Zener diode for beginners. I hope that you enjoy it and learned something from it. And I hope you will subscribe, like, and share this video. Please support our channel because they are trying to take at least 1,000 plus subscribers, possibly in the near future. Thank you so much. Bye bye.